First lesson in atomic structure and nuclear radiation. So we're going to do this today about atomic structure and isotopes, and really just go through and investigate the properties and nature of the atom and the nucleus. So let's start off today with atomic structure and isotopes. Could you please put your date in here so I know when your work did? So we're going to know what the structure of the atom is, and we'll describe what an isotope is and be able to explain why some isotopes are unstable and can decay radioactively. So if you're a chemist or not have a chemist, please just pause the video now and have a go at trying to label this diagram. You should, I would imagine, most of you know already what is going on in this diagram. So take a pause. Okay. So here we have on this diagram, what do we have here? Well, we have on the outside of here, we're clearly looking at an atom. On the outside of the atom, we have the electrons. They're marked with the crosses here. In the middle of the atom, we have these positives and these other particles that have no charge on them. The positive charges are the protons, and the neutral charges are the electrons. So this is fundamentally what I would call a decent representation of a diagram of an atom. One thing that we haven't drawn on here, but you can draw it on now if you want, is just if I circle this central section here, this bit here, sorry I don't have my proper pen for writing on here, this is called the nucleus. So if you could just draw that on there. And the nucleus is the central part of the atom. It contains the protons and the neutrons. And what we're actually looking here, now if you go down below, particularly if you're chemists, you might notice that we've got here the periodic table, a section of the periodic table anyway. So I'm just going to show you how we would decide which atom have we got here. Well, what we're looking at here is we've got 1, 2, 3, 4 protons. 4 protons. So that means we must be looking at this element here. Beryllium, it goes by the name of beryllium. Now, also we've got 1, 2, 3, 4, 5 neutrons. Now 5 plus 4 makes 9, which is what we call this top number here, which is called the mass number. 5 and 4. So actually we're looking at that version of beryllium. Now there are different versions of beryllium. They might have more neutrons or less neutrons. They've all got 4 protons, and if it's an atom, they will have 4 electrons. So normally, when we talk about an atom in its standard state, the protons here always equals the electrons here. So these numbers really are talking about this number at the bottom, the 4, means the protons and electrons, but more specifically the protons, because the electron number can change, and it'd still be beryllium. The top number is all the particles in the middle. They're sometimes called nucleons. We'll come to that word a bit later. So that's 4 plus 5 in this case, and that's beryllium. So let's move on to the next page. And here we are. What we have here is another representation of an atom. You can see the central section here. This is representing the nucleus here, but it's clearly a lot smaller in this one compared to the last one. We can't see the internal structure, which is the protons and neutrons. These outside ones, you can show the electrons. Obviously the scale is totally off here compared to the last one. The electrons, if you did know, are much, much smaller than the protons and the neutrons. So what sizes are we looking at here? Well, if we actually measure the size of the atom, we are normally working in this realm down here, which is 10 to the minus 10 meters. So if you want to get an idea of what 10 to the minus 10 meters, think of a millimeter, divide it into a million parts, and then divide that by 10. And then you're down to approximately somewhere between about the size of an atom. It's actually 1/10 of a nanometer. So nanometer technology is technology really to doing with molecules. So if you took a few atoms together, they would be slightly larger than 10 to the minus 10. They may be about 10 to the minus 9, and really that's what we measure the length of molecules in nanometers. Atom is 10 to the minus 10. So if you went by this diagram, I've done this a few times in class, and I asked people to guess how much smaller the nucleus is compared to the atom, because the nucleus is the central part of the atom. And normally people going on this scale normally say it's about a 15th or a 20th of the atom, just by going on this scale. But actually it's a lot smaller. It's actually, and you need to know this number, 10 to the minus 15 meters. So you've got to really think now 100 thousandths smaller, 100 thousandths smaller than the atom. And the atom was 1/10 of a millionth of a millimeter. So we're getting pretty small now. So you need to move the decimal plate 15 times to go from 1 meter to get down to this size. So gents, what I'd like to do is really just take a look at these two videos and just look at these two diagrams. You've got this model here of the atom, and you've got this model here of the atom. Could you just, in your own words, really compare and contrast those two models there? So the sort of things like that you could mention, there's no structure showed in this one. This one's got the electrons orbiting, and it's quite clear that they've got orbits that are going around. In the other one, I suppose it's more two-dimensional, but it does actually show the electron shells. So actually electrons live in different shells. You actually normally have 2 in the first shell, and you have up to a maximum of 8 in the next shell. Depends on what particular feature of the atom you're trying to stress. Go ahead and do that, pause the video, and then I'll join you for the next section. Okay, next part of this lesson. Really, I've just got some information that you need to know. The first bit we've already done before. The charge of the charge. We showed positive here, but it's actually, for the proton, you need to remember the charge is +1. The electron, you need to know its charge is -1. The neutron is neutral. It doesn't have positive charge or negative charge, so it's a 0. Now, relative mass. Here is a value that I'm going to... The proton has a mass. You could measure it in kilograms. I've got it written down there below so you can read some details. But normally we don't talk about its mass in kilograms. We just give it a mass of 1. It doesn't have a unit as such, but we just say it's relative mass. So when we're in this particular topic, we're going to talk about the relative mass of the proton. The relative mass of the proton is always going to be 1. The other particle that has mass is the neutron. The neutron, which doesn't have any charge, does have mass. Has the same mass as a proton, more or less, and has a mass of 1. Now the particle that in effect has a mass of 0. I mean, it doesn't quite, so you can read this information down here below if you want. That's for you. But normally in this part of physics, the mass of the electron is so low, it's about 1/2000th of the mass of the others, that to all intents and purposes, for what we're interested in here, we just ignore that mass at the moment, and we'll give it a relative mass of 0. So this information here, you do need to know. So it's 1, 1, 0, proton, neutron, electron for mass, and charge is +1, -1. Okay. Now, I'm going to move on and try and describe now what is a isotope. So I've got another slightly different representation of a model. You can see our protons and neutrons in the middle, and we've got the electrons represented as red dots around the outside. And what you might notice in all the diagrams that I'm going to come up to now, I'm always going to keep the number of protons and electrons the same. That means for the next few diagrams, that means I'm dealing with an ion, an atom, not an ion. An ion is an atom that's lost electrons. So just for the next few diagrams, while I discuss what an isotope is, because an isotope is really defined by what goes on in the nucleus. So if you just count up, I'm just going to show you how we would match this atom into one of these or something similar. How would we label this atom? Well, this atom has 1, 2, 1, 2, 3, 4, 5 different 5 protons in the middle, and it's also got 1, 2, 3, 4, 5 neutrons. But because it's got 5, I'm going to label this with a 5 at the bottom, and that 5 here, and this 5 means it's got 5 protons, and that means it's boron. So I'm going to put a B in there. So what should the top number be? Well, the top number represents here the total number of what we call nucleons in the middle. That's protons plus neutrons. So 1, 2, 3, 4, 5. And that actually is represented the same as the one on the periodic table. It's boron 10. It's boron 10. Okay, let's go on to do another one. Here we can see, let's count it up, have a go. If you'll need to pause the video, and let's count up and see what we're looking at here. 1, 2, 3, 4, 5, 6, 7. 7 protons. So what do you think we're looking at in it? Which element are we looking at here from the periodic table? 1, 2, 3, 4, 5, 6, 7. We're looking at nitrogen. Now, is it the same version that's on the periodic table? Let's have a look. 1, 2, 3, 4, 5, 6. So 6 and 7 doesn't make 14. It makes 13. This is not nitrogen 14 that we find on the periodic table normally. This is nitrogen 13. 13 because there are 13 particles in here. And it's nitrogen because 7 of them are protons. So this is really what we would call an isotope of nitrogen. It's just a different version of nitrogen because it doesn't have the same number of neutrons as the normal version of nitrogen, or the most stable version of nitrogen, which has 7 neutrons. Okay, let's try another one. Have a go at doing that yourself. Have a pause of the video if you want to before I do the reveal. Okay, first off, this should be an easy one. I've got 2 protons, so I know I'm over here. I'm looking over here at helium. Must be some type of helium. Is it the same on as the one on the periodic table down here? 1, 2. There's my 2 protons, and 1, 2, 3. So notice I've got 2 electrons because I've got 2 protons. So the bottom number must be 2 to go with the 2 protons. Because it's 2, it must be helium. What's the top number? The top number is the mass number. That's the number of the particles in the middle. So that must be, in this case, 5. That's helium 5. Again, it's an isotope of the version of helium that's on the periodic table. Let's go through these a bit quicker now. Have a go. Pause the video if you need to. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You've got 7 protons, 7 neutrons. First of all, 7 protons tells us it's nitrogen. And what top number? Nitrogen 14. Very good. Just 1 proton. Just 1 proton and 3. So that tells me the numbers are 1 and 4. 1 and 4. 1 because it's 1 proton and 4 here. And what element are we looking at? We're looking at hydrogen. Hydrogen, because hydrogen is the only element with one proton. Slightly larger one now. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 protons and 10. 9 protons and 10 neutrons. That must make the top number 19. And the bottom number is 9. What are we looking at here? Boom, there we go. Fluorine. Very good. So, we just maybe jump to this page here now, and we can just write this in. Isotopes are nuclei that have the same number of, what word goes in here? Same number of protons, but a different number of neutrons. That's what you want to write in there. That's the important bit for there. Same number of protons, but a different number of neutrons. Very good. Okay, so I just wanted to spend a little time on this now. Explain why some isotopes are stable and some aren't. So I'm going to talk about this, and you can just write something down in your own words. It's not a major thing. If I just scroll through some of these nuclei that we've gone through, we looked at nitrogen 14, nitrogen 5, helium 5, nitrogen 13. What you'll find is normally the more number of protons, the more number of neutrons you have. And pretty much there are just certain, in physics, I'm often fond of saying physics is the study of the physical world. So physics is the study of what is. There is no magic book that has been handed down to tell us what should be, how elements and atoms are, that they are. So what we've actually done in the periodic table is sorted out the elements by their most common versions. And we actually find that if you move away from that 1-to-1 ratio, then actually those atoms just split apart and they're just not stable. And so we just don't find them around in nature. Maybe this little representation might help. This is a little chart that shows neutrons against atomic number protons. So you can see a lot of the common ones on the periodic table are these ones in the grey. If you're looking at these isotopes up here, all the heavier version of nitrogen up here, and you've got all the lighter versions of nitrogen down here, so these have got less neutrons and these have got more protons. Well, it just so happens that some of these versions aren't particularly stable and they fall apart. And that's all, if you want to explain why that is, you really need to be getting into university level physics, because it goes way beyond really GCSE. All I want to do at GCSE level is just explain to you that there are particular versions that seem to work, and there are some that don't. So if you could just write down, really explain why some isotopes are stable and some aren't. Really, it's something to do with the ratio of protons and neutrons. It needs to be just right. Smaller ones, if you want to know some details, normally have a ratio of about 1-to-1. If you look on the periodic table at the larger elements that are stable, they normally have a ratio that moves towards about 1.5 neutrons to 1 proton. Okay. Now, let's jump back to here. You can have a go at doing this little task now. So, complete here for number of positive charges, number of negative charges, overall charge, and whether it's an atom or not. To do this section down here, which ion shows a positively charged ion? Well, what you've got to do there is look at this diagram here, and if it's got more protons than electrons, or less protons than electrons, then that is what we call an ion. An ion. An ion is really an atom that's lost or gained an electron. So that's really what you could say there. An atom, an ion, is an atom that has lost or gained an electron. Okay. For your final task, assuming these are all atoms, what I'm saying here is that the number of protons is always going to be equal to the number of electrons. So protons and electrons are always going to be the same. You can get the proton number or the atomic number, which is another word, so that's going to be the same as our atomic number. Number of protons, number of electrons are all going to be the same, and that's always going to be this bottom number here. You should know how to get the number of neutrons from here, so please complete this table. The final column is just for the chemists only, a little bit of fun. If you know how the electrons are organised, feel free to have a go at doing that, and otherwise I will see you in the next lesson.